Good morning and welcome. I'm Jim Green, and I'm going to talk about some of the really tremendous capabilities that a new vehicle that's coming up called the Space Launch System has in the NASA arsenal. So let me first mention what a wonderful industry collaboration with NASA has created a new launch vehicle, the Space Launch System, and it is tremendously capable. Now, you know, it's being designed as a human-rated vehicle to take humans to the moon and then on to Mars, but it also has the capability of taking a variety of other payloads, and with a huge, not only C3, but mass capability. One of the things that we're also developing is Boeing is developing this EUS, which is the exploration upper stage, that will then also really enhance our ability to get things all over the solar system and even out of the solar system. When you talk about the lift capability that the SLS has, it's really 3 times anything that we currently have in our arsenal. And this has some really important and unique capabilities that I'm just going to have a few minutes to be able to really touch on. And in particular, as it relates to planetary systems. In the previous session, if you've had an opportunity to see the fabulous collaboration internationally that NASA and ESA and many of the other countries have in launching JWST, you recognize what an origami kind of thing that's happened to be able to use these segmented mirrors and put it in a very tight fairing. But with the SLS, we have the opportunity to really create larger fairings, 10-meter fairings. So in many cases, as this capability is continued to be maintained and used, we can also think about other missions in the sciences that can take advantage of the large capability of a 10-meter fairing. Well, the capability of enhanced C3 and large mass really enables us to create the human exploration program beyond low Earth orbit. But what I want to do today is emphasize its other capabilities by giving examples of how it can be used to really enhance science. And in the examples I'm going to do, I'm going to talk about planetary science. These are going to be multi-mission targets. I'm going to talk in particular about the ice giants. These are things that are the top things in the planetary decadal. I also want to talk about how the SLS could be used in heliophysics. And that means taking spacecraft that are completely capable of making enormously important measurements out past the heliopause and into the winds of other stars. And then, of course, in the astrophysics area, there's so many different things. As I mentioned, with the larger fairing, larger telescopes are really quite obvious. But there's a number of other things for which the mass capability of large lift capability of the SLS could really enhance our abilities to deliver equipment to the moon and create far-side observatories that are completely important in the areas of astrophysics and also space physics. Planetary Science just released its Decadal, and in NASA, we asked the National Academy of Science for some objectives. What are the top strategies, the top fundamental questions we need to answer in each of the fields? And this year was the opportunity for Planetary Science to release its Decadal. Now, in that is quite a list of really important objects that we needed to be going after. And they're divided up in areas of large cost, medium cost, and smaller cost. And in the area of the large cost missions, like flagship missions, the top rated mission is Uranus, going out to one of the ice giants. Now, if you remember the Voyagers, what we know about the ice giants in terms of making in situ measurements up close and personal has really been Voyager 2 and only Voyager 2 flying by Uranus and then through Neptune, and that was many decades ago. And so this is one of the reasons why it's also one of the top missions. But there's other activities like Enceladus and Europa lander, Mercury lander, things that are really significant in terms of the amount of mass that has to be delivered to these objects. Ongoing missions in the Planetary Decadal said we've got to keep going with our current program, and of course the top mission to go out to the outer solar system that we're developing next is the Europa Clipper. Now at one time, if all the schedules would have aligned and everything would have been great, an SLS was thought about being used for Europa Clipper. And instead of the multiple gravity assists that Europa Clipper has to do now on the inner part of the solar system and taking 8 to 9 years to get out to Europa, an SLS would be able to put it out there in 2.9 years. So direct trajectories are tremendously important. That gets a mission to its target and begins the operation. And of course that means as you go out to the outer part of the solar system, the faster you can get out there, the more science you can do in a timely manner. You know, decadals are all about saying these are the missions that we need, these are the fundamental questions we need to answer, and please get it done in a 10-year period. Well, when it takes a significant amount of time just to get to the target, you're already well behind in being able to meet your objectives in these kind of activities. Also, completing sample return. Launch vehicles for the sample, a complete set of sample return missions haven't been announced or defined yet. And so that program is developing concepts that may indeed need heavy lift capability. And so important trades in the future will have to be made. And so we'll have to take a look at what's happening and be on the lookout for that. And then, of course, there's the New Frontiers targets, this middle tier set of missions. And this is quite rich in the areas of landers and orbiters and sample return systems. So a tremendous opportunity here could be had if indeed we continue to use the SLS, not only for human exploration, but indeed for robotic exploration. I can't overemphasize the importance of timeliness. When you look at the opportunities to go from the Earth to the outer planets with the large C3, you end up with 2.5 years to 2.9 years to get to Jupiter, to 6 years of Saturn, 10 years and 12 years. And so these are really important opportunities for us that really cut down, one, on the fact that your spacecraft has a set lifetime. It's amazing. We take our car in for refurb every 6 months or so, sometimes even more often, and yet we expect a spacecraft to last 10 years before it starts even doing the science. So this is really a game changer in many ways. The concept of the large mass, the ability to put into orbit an enormous payload, can then be brought up and thought about as segments. Let's launch more than one payload. And in this particular concept, here's where we launch from Earth. We get a gravity-assisted Jupiter dropping one system off somewhere, but then going on with that gravity assist to another location. So the concept of then being able to accomplish more than one objective, perhaps a flagship plus a New Frontiers, or maybe a couple discovery missions. Now that opens up additional possibilities, indeed, for planetary science. In 2017, I was head of the planetary science at NASA, and I commissioned a study with JPL to look at the ice giants, to look at what are the things that we need to know, what are the important things that we need to then define, and then how do we accomplish that through a variety of mission scenarios. And I wanted them to include the option of using an SLS. The European Space Agency responded with 2 additional reports soon after that, one about probes, the ability to take probes that could be dropped off. And this is exactly in the same ilk that we did with ESA on Cassini. Cassini had a main mission orbiting Saturn and then dropped a major probe off on Titan. Well, we were mass constrained. Imagine an opportunity where you not only have the main spacecraft, but several probes. Perhaps a Triton probe in addition to orbiting, getting in orbit around Neptune. Or even two major missions, one going to Uranus and one going to Neptune. If the gravity assist capability was appropriate, that you could actually get to both of those planets in one trajectory. Well, the ice giant study that we accomplished did indeed have several trajectories, opportunities in the late 20s, early 30s to be able to launch one mission, get a gravity assist at Jupiter, go on to Uranus and to Neptune with two spacecraft that could be launched but could only be done with an SLS. So this is tremendous capability for the scientific community. Well, of course, the scientific themes for ice giants are really about studying their interiors. We don't know much about the interior. These things are called ice giants because they have in their atmospheres a very different composition than the atmospheres of Saturn and Jupiter. These ice giants have many more volatiles, water, ammonia, etc., where the gas giants are much more hydrogen and helium. So atmospheres and understanding how these atmospheres come about on these giant planets in the outer part of our solar system, and in addition to really teasing out the compositional aspects of it. They both have magnetic fields. Nearly all planets have magnetic fields. It's one of the most fundamental properties we think of the generation of planets, whether they're terrestrial planets or gas giants. It seems to be very important. Moons, of course, these ice giants have collected several really fabulous moons, one of which we believe, like Triton around Neptune, is a Kuiper Belt object. We spent 9 years going and flying by Pluto, flying by it. We didn't orbit it, we didn't land on it. And yet that moon, or that dwarf planet was such a fascinating object. We really need to understand better these Kuiper Belt objects. And here's one orbiting Neptune. I can imagine a mission going there, dropping several probes off, where we actually land and rove on Triton, a Kuiper Belt object. It's right in our backyard. And of course, they have rings. Uranus and Neptune have rings. They're very tenuous. Just like Jupiter has rings that are very tenuous. If you've seen the JWST image of Jupiter, I'm sure you'll go, wow, what is that? It's a ring. It's leftover material that's been accreting to the planet. So both Uranus and Neptune just have a tremendous number of really important things that we want to be able to look at. And they're very highly variable, actually, in their climatic patterns. We know that because JWST will start looking at these based on Hubble data, which tells us that over periods of time, both Uranus and Neptune have a variety of atmospheric storms. And so what are they like, and how is that occurring? And what is the connection of these storms with the solar input? So quite a bit of really fascinating objects they have become, and we really want to understand how they were accreted. What is the interior of Uranus and Neptune? Is it a rocky body? Is that how it started out? Now, for Saturn and Jupiter, we see a much larger core, and it's much more nebulous, and it's harder for us to really figure out and understand. But we have an inkling that these may be rocky cores that start these ice giants in the distant region, but we're not sure. And so, indeed, studying these were really important. The other aspect about Uranus and Neptune are they are an important size and an important type, and it looks like most solar systems beyond Earth have these mini Neptune-like objects. We also can call them super-Earth if they're more terrestrial-based. And so this kind of is the archetype of planets that we see all over the place orbiting stars. We just need to know more about them. So indeed, a deep space mission could indeed with a gravity assist, take probes, orbiters, both to Uranus and Neptune, along with probes, dropping them in the atmosphere. Now, this also forms a tremendous opportunity for partnerships. You know, where we can partner with other space agencies, where they build aspects or components that are part of a larger mission. You know, probes are extremely important for us to be able to then deposit, understand, take a variety of measurements that you can only make when you take an object and interrogate it with something that will be destroyed, and you get unique information back. It's the only way to do it. And so by sharing the cost, you also have the opportunity to build a much stronger program by working together with multiple agencies. Now I want to shift gears a little bit to another area or discipline in the Science Mission Directorate at NASA, and that's called heliophysics. And of course, heliophysics is really about the study of the sun and its influence throughout the solar system. And the sun has a magnetic field, and this magnetic field goes through cycles. We know about the sunspot cycle. The result of that magnetic field is it extends way out beyond the planets. And that location where the magnetic field of the sun stops, and on the other side of that are the winds of other stars, we call the heliosphere or the Heliopause. And of course, Voyager 1 and 2 have passed through the Heliopause. And so for the first time, we have an opportunity with those two missions to understand the limits of where that Heliopause is, how it might be changing, and some basic characteristics of it. But I have to tell you, Voyager 1 and Voyager 2 are really very crippled. Not all their instruments work. They weren't designed to go out to the outer reaches of our heliosphere and into the winds of other stars. They don't have the right instrument complement. What they have done is that initial survey that allows us to say, here are some of the basic boundaries, and some basic information that tells us that we need to learn more about these boundaries. So NASA's commissioned another study called Interstellar Probe. How can we launch something that really interrogates this area? And indeed, Europe has come back with another complementary study of how we could also work together in this grand venture of going out to the outer part of our heliosphere. Well, this is really a tremendous opportunity because we don't really understand a lot about this particular region. As I said, the Voyagers have said it's about here, about 125 astronomical units away, okay, where one astronomical unit is the distance between the sun and the earth. So it's very far out there. And the composition and the increase in cosmic rays and all the other elements that come from winds of other stars can be interrogated if we can go beyond that heliosphere and we can really understand how the sun moves in the galaxy, okay? We see other stars with heliospheres. We call them astrospheres. If you actually look carefully at the latest image from JWST, you can sit and pick out the astrospheres, all right? So magnetic fields are generated by suns. These suns have an influence that go well beyond their basic orbiting planets and interact with the arms, the spiral arms of the rest of the galaxy. It's a fabulous area to really go study. Now, there's three basic questions a mission like this needs to answer. And they're really all about what happens on the inside of that boundary just before you move through it, and what happens on the outside of that boundary after you move by it. Now, we always thought we understood that because there's boundaries of magnetic fields and winds and plasmas all over the place in our own solar system, like the Earth's magnetopause. But we're finding that the physics in these areas are actually different. We don't really understand them as well as we thought. And so the concept of being able to go through making high-resolution measurements as you punch through the heliosphere is really going to give us an understanding of perhaps a new way the plasma is interacting with magnetic fields in these distant regions. And then, of course, what's happening in that interstellar medium? What's going on with the clouds of materials that move in the spiral arm with us? We're moving out of one cloud right now and into another. We've gone back in time about 2 million years and moved our sun and computers and its heliosphere back into an earlier cloud and found that the pressure has really crunched down the heliosphere, almost to where the Earth is. Can you imagine a heliopause within the orbiting parts of our planetary system? And what does that do? We have found iron-60 in the ocean at 2 million years ago. We believe is coming from a supernova, and that was a shocker. And now we understand that perhaps the only way that could have occurred is our astrosphere, which has protected us as we've gone around the galaxy, was shrunk to the point where we were hammered by explosions of nearby supernova and pelted with all kinds of different types of radiation. These are the kind of things we'd like to understand more, and Interstellar Probe is indeed designed to do that. There's some launch windows coming up in the 30s. Highly capable systems are being thought of and planned. And what we want to do is we want a 50-year mission that doesn't go just 100 AU like the Voyagers, but 500 AU and beyond as possible. And the only way we're going to be able to do it is use the C3 capability, the launch capability of the Space Launch System. Really a game changer. Now let me end real quick by mentioning another wonderful opportunity for us to be able to leverage and use the SLS, and that's the ability to bring more mass up to various locations, and in this case, perhaps the moon. You know, we just finished a fabulous conference at the Kennedy Space Center in June where we talked about some unique science that we can do on the far side of the moon. The far side of the moon? Really? What's that all about? Well, the far side of the moon, as shown in this Mercator projection, is really radio quiet. You know, the Earth is using radio frequencies now like crazy. You know, not only for tracking, for many different services on the ground. Communication, of course, is the top use of these radio waves, and that makes anything you do from the ground or even from space, if you don't hide yourself from the Earth, problematic in a variety of radio frequencies. You know, from tens of kilohertz on up to megahertz and into gigahertz sometimes. Now, even though the Earth has radio windows, and there's actually some places in the radio spectrum that those radio waves cannot reach the surface of the Earth, and that, once again, opens up a new part of the spectrum. The concept of being able to go to the far side of the moon then becomes a no-brainer. On the far side of the moon, we're completely hidden by the radio interference from the Earth, and it's radio quiet, as shown in this particular example, where the far side of the moon is right at the center of this Mercator projection, and then the circles represent the amount of radio quiet you receive. So, far side observatories in the radio sounds pretty tough, and indeed it is. It has many engineering challenges. It also is, what kind of frequencies do we need? So we want to really understand the frequency ranges that we'd be able to support, and whether we'll do it with an array or whether we'll take advantage of the large craters by using that kind of structure to support more solid dishes. Those are engineering details, but each and every one of them require considerations of heavy lift capability to bring materials to the moon, let alone deploying them. With humans in the area, the ability to go to a location after a radio observatory has been up and running, service it, and be able to continue bringing the fabulous data back from those enables our capabilities to really be enhanced over long periods of time. And indeed, our objective of going to the moon is learning to live and work on a planetary surface, not like the Apollos, not for a day or two and return, but for weeks to months. And so, is this a perfect opportunity to be able to deploy instrumentation in the radio frequency area that opens up a new area? And the answer is absolutely yes. Now, there's several kinds of things that we'd be able to do in this area. JWST, what it does is it looks back in time at the early galaxies, okay? And the early galaxies are really formed in this particular area. That's where JWST can look at. It can't look beyond that. Beyond that is an area called the Dark Ages. And the Dark Ages are where neutral atoms are being put together. Hydrogen captures, a proton captures an electron and it becomes hydrogen. And is dormant, except the electron will move every once in a while, flip its spin, and when it does that, it emits a 21 centimeter line. So the dark ages can be probed at a certain frequency range. But if you want to understand what happened at the time, 13.7 billion years, you need to understand how 21 centimeters has been Doppler shifted, and it's Doppler shifted in the radio frequencies, from 30 megahertz to 3 megahertz. Fabulous opportunity to look now beyond what JWST is doing to the early formation of matter before they even become stars. Star formation is quite important. We're now beginning to understand how the material accretes, falls in, begins a process of nuclear fusion at the very center of the star. But the star goes through some really unusual phases. Gas jets are flying out of the polar regions. And in many cases, these are seen in the radio frequency areas, and we can get a better understanding of star formation. By looking at the sun at certain wavelengths in the radio frequency, we actually are looking at the upper layers, which is the beginning of potentially some really intense space weather events that start at the sun and propagate to the Earth. Well, space weather events, although we understand them now more and more, we haven't really seen in the modern era what the sun can put out. They can be really phenomenal events where huge currents arise in our ionosphere based on the interaction of huge amounts of solar wind material and magnetic fields hitting our magnetosphere, forcing it to rearrange itself, producing aurora that goes through Canada, United States, Mexico, down through Central America and into South America. Those auroral events have been seen in the past. We have many indications, Japanese records, Chinese records, tree rings even, that tell us superstorms are an event that's on a different cycle, hundreds of years cycle. And of course, those aurora at the bottom produce immense currents, which then produce EMI events here on Earth. Understanding what's happening in the atmosphere of the sun as early as we can is really critical to getting important information about space weather so that we can react through these events. Now, I mentioned magnetic fields are one of those fundamental things, fundamental aspects of magnetospheres. And yet, when you look at the spectrum, you see that below 40 megahertz, our Earth-observing systems do not see those radio waves. They are actually reflected off our ionosphere and don't make it to the surface. But indeed, from a radio array on the far side, we can actually look at radio emissions from not only the magnetospheres of our own planets in our solar system, but from magnetospheres of other planets orbiting other stars, which then can enhance our information and understanding of whether those planets are habitable or not. It opens up a whole new field of study that relates the fundamental formation of terrestrial and gas giant planets producing magnetic fields, therefore magnetospheres, and gives us a much better understanding of their strength, their orientation, and how much energy totally is being deposited in particle radiation on these planets. And these radio waves are generated in hollow or indeed full cones, for which then when we study those and look at them can really tease out various aspects of the planet's magnetospheres. Black holes. We were astounded by the Event Horizon Telescope observations of black holes. These black holes are telling us that there's a disk of material accreting, falling within the event horizon, being swallowed. And we're creating these images because we have large baselines. And you can see the baselines covering the surface of the Earth. But with a radio observatory, you change the whole dynamics. Here's a new part of your baseline. And it can observe for longer periods of time and move and increase the size of your baseline over time, which really enhances the kind of information you bring in, allowing us through these kind of simulations of the baselines we're talking about to understand intense details of these collapsing clouds that orbit black holes that tell us that they are there and they are real. So, science objectives and the radio frequency ends all go from planetary magnetospheres, stellar radio emissions, all the way to imaging black holes and star formation. So it's just a whole set of things, and of course, looking at the early part of our solar system called the Dark Ages. So, the SLS can deliver large mass structures in addition to multiple spacecraft with multiple elements, supporting science and human exploration, and we should take advantage of it. It now opens that activity up. So let me just summarize that indeed there are major advantages in using an SLS. It's really a super heavy lift vehicle. We can co-manifest within the Science Mission Directorate. We can co-manifest internationally, drawing in more partners. I mean, JWST, as we saw just in this last session, was such a tremendous success because of the international partnerships. We need to keep that going. This is so important part of our space field. And so its flexibility enables it to be what we think is an important trade study, having it available for us to make those important trades, to use it as a potential launch vehicle, and take advantage of its uniqueness. Now, I want to mention two other things. One, as we all know, our first SLS will be launching Artemis 1. The window opens up Tuesday. But you may not know that on Monday, we have a very small spacecraft moving very fast, 7 or 8 kilometers per second, that's actually going to hit an asteroid and move it. If that works, and we understand what happens, we then are going to understand that one time in the future, a larger mass object will need to be moved, and that means we're going to need more mass to orbit and a higher C3 to defend this planet. And I think the SLS needs to be part of that trade study. Thank you very much. I think I have time for some questions. Yes, sir.
Yeah, Jim, I'm just wondering, you mentioned the radio telescope benefit from the distance between the Earth and the Moon. Again, large masses, I know the LIGO detectors are rather long and massive. Is that something else that we could think about someday, getting a LIGO detector on the Moon that could be integrated?
Ooh, yeah, for gravity waves? Yeah, yeah, that's a great idea. Yeah, it's a great idea. I mean, there's so many things like that. So once you have the capability, it allows you then to step back and look at the fundamental physics, and then use the high mass, high C3 to be part of your trade study. Yeah, it's a great idea. Any other questions? Okay, if not, I'll turn it over to the next speaker in this series. Thank you very much.